Hi, Mana Kasale.
Hi, how are you?
I'm good, thank you. How are you?
I'm fine. It's good to
That's
hear your
good.
voice.
It's been long.
For real.
Where have you been hiding?
I've been around.
Those who've been around have been hearing from them. Number, you people have been hiding.
Not really, because I don't have your number, that's why.
Oh yeah, that's why.
Yeah, unless you text me on WhatsApp, then no. We'll be in
Okay,
touch.
we'll text you.
Sure.
We'll text you. How have you been though?
I've been fine. Generally, I've been okay. How about you?
That's
The
Pardon?
I mean the quarantine thing at Cite. How is it?
So. I'm managing anyway.
Resume recording. Okay. Thank you very much for that. Thank God we didn't do so much. Okay, so we're going to use the composite derivate. So since we have euro in terms of phi, in terms of phi, we are going to have d de rho sur d phi. It's like we are going to derive euro in terms of phi because we have an expression for euro in terms of phi. But then since we have introduced d phi here, we'll need to introduce this expression up here. So d phi sur dt. These are the same because this défi and this défi up here can simplify and will remain with de euro sur dt. So we are going to break it down in this way. Okay, now it's become composé. We have broken it down in that way to help us derive euro. And then défi sur dt is simple. The way we wrote rho point, the way we wrote z point, the way we wrote x point, the way we wrote y point is the same way we are going to derive phi par rapport au temps. We just write phi point. Okay, that's why we have this phi point here. And then we have this expression now to work out de euro sur des phi, which I explained to you guys last week how to calculate this. And we found that de euro sur des phi was equal to what? And someone please tell me. When I told you the dérivée d'un vecteur unitaire heureux par rapport à l'angle phi is equal to a rotation of 90 degrees. So when heureux, we derive heureux par rapport à l'angle phi, we are going to make it rotate 90 degrees. And it's going to become what? I explained this to you guys, I emphasized it. On est ensemble. Are we together?
We are together.
Yeah, so what's the derivative of heureux par rapport à d phi? What's it going to give us?
E theta.
Not exactly e theta, but you are close.
Negative sine rho plus cos theta.
Okay, you have the answer, but the angle you are mentioning is not the right angle. You are confusing two angles. It's not theta,
negative sine theta.
Not theta. So far, we've looked at two angles. We've looked at theta, and we've also looked at another one, which is
Negative sine phi plus cos phi.
yes, negative sine phi suivant I plus cos phi cos phi suivant J. And this gives us which vector unitaire? Ooh la la, ladies and gentlemen, we did not revise the work. Phi. We looked at this and I explained to you guys, I said, when you derive heureux par rapport à d phi, it gives you phi. Phi. It's there in the notes. This part should be the last part in this other PDF. This part here, we explained this. We got the expression for heureux as cos phi, I plus sinus phi, J. Then we derived it par rapport à phi. It gave us this expression, moins sinus phi, I plus cos phi, J. And we remarked that this expression here that we found after deriving heureux was equal to the expression for e phi. And we finally concluded that de heureux par rapport à l'angle phi gives us e phi, gives us the vector e phi. And then we generalize this rule. We said, when we derive heureux par rapport à d phi, it's like a rotation of 90 degrees. And we know that heureux and e phi are orthogonal to each other, meaning they are 90 degrees to each other. So if I'm going to rotate heureux 90 degrees, I'll be rotating it into e phi. So it's going to become e phi. And if I rotate e phi again 90 degrees, it's going to go in the opposite direction of heureux. So it's going to become minus heureux, and ainsi de suite, just like that. We talked about this last week. These are the principles you are going to be using when doing the calculations you'll be doing in mechanics. So pay attention to them, pay extra attention to them. And these are the things that we'll be using today. That's why I emphasized yesterday that we make sure we revise what we did last week. But since we did not go through the work and we're going to waste time explaining the same things over and over again, when we can profit from this time to advance so that we can finally do some questions that will help you guys understand further. So let's revise. Emphasis, let's revise. So, de heureux d phi gives us e phi. Is that clear?
Yes, it's clear.
Okay, so de heureux gives us d phi. So we have e, so from this expression here, when we derive de heureux par rapport au temps, it's going to give us e phi times phi point. Okay, it's going to give us e phi times phi point. So finally, our expression for v and in the coordonnées cylindriques is going to be equal to de OM sur dt, which is going to be equal to, so now when we derive the rho par rapport au temps, it gives us a rho point. So we'll have, when you see this expression in the box here, rho point suivant heureux plus, then we come to the next part here, it's going to be rho multiplied by what we found when we broke this down. It gave us a phi point multiplied by e phi. So it will be rho phi point suivant e phi plus the last expression here, when we derived z par rapport au temps, it gave us z point. So we'll have z point suivant k. So this is the expression for the Vitess in the cylindric coordinate system. You are supposed to know it by heart, but don't memorize it just yet. Know how to derive it, how to get to it. Yeah, so practice, get your vector OM equal to rho heureux plus zk, then derive that expression and reach at the Vitess or arrive at the Vitess and continue with it. And even when we'll be doing exercises, work with it, and then it's going to stick in your mind. Don't go straight into memorizing it without knowing how to derive it. But that's the expression we have for the Vitess dans le coordonnées cylindriques. C'est rho point heureux plus rho phi point e phi plus z point k. Est-ce que c'est clair?
Oui, c'est clair.
Love. Then the modulus, as usual, you just get the coefficients of this vector unitaire. We'll get rho point carré plus rho phi point carré plus z point carré, and le racine carré. It's like you do the square root of everything. Then in the square root, you put rho point carré plus rho phi point carré plus z point carré. Just like we had x carré plus y carré plus z carré. La même chose. So it's like this for the modulus. Then yesterday, not yesterday, but last week, we introduced the notion of coordonnées polaires, and we said the coordonnées polaires is just the same as the coordonnées cylindriques, except for the fact that in the coordonnées polaires, z is equal to 0. Okay, it's like that's moving in the horizontal plane. So whenever they tell you coordonnées polaires, just remember the coordonnées cylindriques, but with z equal to 0. As you can see here, cas particulier, si z égale à 0, le mouvement de la particule est plane, rho, phi, coordonnées polaires. So this the coordinate, the z coordinate will be equal to 0. So we'll just be left with these two, rho point e rho plus rho phi point e phi. And that will be our Vitess in the coordonnées polaires. Then the magnitude of the Vitess, comme d'hab, you just get these coefficients, rho point carré plus rho phi point carré, and with a racine on top or square root. Is it clear?
Oui.
Excuse me, can you repeat here the network was cut?
Okay, I was saying coordonnées polaires. Whenever you hear coordonnées polaires, just think of coordonnées cylindriques, but with z equal to 0. The z coordinate in the coordonnées polaires is equal to 0. So it's like you are just in the horizontal plane. There's no vertical plane because the z axis is the vertical, represents the vertical axis. So it's the vertical plane. But in the coordonnées polaires, we do not have the vertical plane. We are just in the horizontal plane because z is equal to 0. That's the rule of the coordonnées polaires. C'est la règle. Z égale à 0. So this z coordinate here that we have is going to be equal to 0. The z point k will be equal to 0. So we'll just be left with rho point e phi plus rho phi point e phi. Okay? Clear? Okay, I hope it's clear. This one is quiet. As I told you at the beginning of our lesson today it's mostly calculations. It's just calculations we'll be doing because we'll just be deriving expressions for Vitess and acceleration, for the velocity and the acceleration. So it's just mostly calculations. So make sure you prepare your faculties for mathematics in your heads, okay? Because today is going to be a lot of calculus and a lot of trigonometry. So now we go to the coordinate spheric. We have the expression for the velocity in the coordinate Cartesian. We have the expression for the velocity in the coordinate cylindrique. And now we are going to look at the expression for the velocity in the coordinate spheric. Okay? And we know dans la base ER, Eθ, Eφ, associé aux coordonnées sphériques. We looked at this when you're in the coordinate spheric. You work with the base ER, Eθ et Eφ. Le vecteur position de la particule s'écrit OM égale R, ER, rather. We looked at this, R, ER, because M is there and we have our origin there, O, and then we have this vector unitaire ER oriented in this direction. So we can already define it directly. I explained this. It's not like in the coordinate cylindric where you have to take a long cut because it goes like that, then like that. But in the coordinate spheric, you can go directly from 0 to M because you have a vector unitaire oriented in that direction. So you can properly define it and someone can understand. And we have the magnitude of this distance between O and M being equal to the radius formed by the point M, which is R. So our vector position OM becomes R, ER, okay? R, ER, like this. That's the vector position from there to there. Directly, you just go from there to there. You'll be moving a distance of R in the direction of ER. That's what this is telling us. And as usual, for us to calculate the velocity, we are still deriving the vector position, OM, because the vector position gives us the displacement or the distance. And we know that velocity is the rate of change of displacement, okay? That's why we will be deriving the displacement, which is OM, to get our velocity. We'll be deriving it with respect to time, because when we are calculating speed or when we're calculating velocity, we just want to know the rate of change of distance or of displacement with time. That's why we are deriving OM par rapport au temps for us to calculate V. So the expression still stands, vitesse ou bien V de M par rapport à R égale D de OM dt. So we have OM being equal to R, ER, and as usual, we have a product here. So the rule that's going to apply, as you already know, is the product rule. So we're going to have first dr over dt, ER plus R d de ER over dt. And as usual, R is simply just telling us the distance between that and that, between O and M. It can be anything there. We do not really have an expression for R, but it's just telling you that it's anything here, it can be anything there, okay? So when we derive it, we just write R point to show you that you have derived the distance between O and M. All right, just to show you that you have derived it, we just write R point to show you that it's the first derivative. So when we derive de R par rapport au temps, we just write R point, ER plus R. Now we'll be deriving de ER dt, okay? Der dt, we're going to derive it. This one is not as direct because we have an expression for ER. So when we come to the expression for ER, let me look for it in this PDF. Il est où? Ou bien elle est où, l'expression? Okay, so we have this expression here. Can someone tell me this expression is in function of what? Or in terms of what? What are the variables in this expression? ER is written in terms of what? Is it in terms of time?
No, we'll be given in terms of angles too.
In terms of what?
Angles.
Yeah, in terms of angles. Which angles are those?
We have theta, phi.
Lovely. Exactly. That's true. As our friend AL has remarked, the expression for ER has been given to us, or we found it in terms of the angles theta and phi, not in terms of time. So we cannot derive d de ER par rapport à dt directly. No, we cannot go directly about it because we do not have the expression for ER in terms of time. So we are going to use the same principle we use when we're deriving euro, the same principle we used. We are going to decompose it, okay? So since we know that ER has been given to us in terms of theta and in terms of phi, we are going to decompose this derivative so that we can derive ER par rapport à theta and par rapport à phi, so that we can easily derive it because we have the expression written in terms of that. That's what happens. That's what happened here now. This step, they are saying d de ER par rapport à dt is equal to, first of all, I explained to you guys, I don't know if it's last week or the week before, the partial differentiation. That should have been in the first week. We looked at partial differentiation, okay? Partial differentiation is when we have more than one variable in an expression. And I told you guys that when you're deriving using partial differentiation, you just derive with respect to one variable while keeping the other variable constant, plus you derive with the other variable while keeping the first one constant. It's that simple. So even here, because we have ER written in terms of theta and in terms of phi, both of them are varying. So what we're going to do is we are going to first derive it par rapport à theta while keeping phi constant. Then we're going to derive par rapport à phi while keeping theta constant, which is what we are doing here. Notice this plus sign here. It's the same thing. We are just starting with theta first of all, while keeping phi constant. Then we'll come and derive par rapport à phi while keeping theta constant. So we'll have d de R par rapport à d theta, and then we are going to multiply by d theta sur dt, so that we do not change the nature of the expression, plus here we'll have d de R par rapport à d phi multiplied by d phi d theta. And as usual, d theta sur dt is just going to be theta point. And d phi par rapport à d theta, par rapport à dt, sorry, not d theta, but dt, is also just going to be phi point, tout simplement. You just write phi point, theta point. It's these guys now, d de R par rapport à d theta and d de R par rapport à d phi. that are going to make us work a bit. So we are going to begin with this first one here, d de ER de theta. So we are going to derive it. So since you guys have not been revising, today we'll be working together. So I want you guys to get this expression, ER. I want you to derive it par rapport à theta. Derive it par rapport à theta. Okay, so if I say par rapport à theta, meaning phi should be constant. Treat phi as a constant. Derive it par rapport à theta. You have 3 minutes. The time is 15:44. At 47, I'll expect a response from you guys. So, ER, d de ER par rapport à d theta. Let's go. We have 3 minutes. Okay, so you can just write the answer in the chat box when you find it. Just write cos between brackets, whether it's theta, whether it's phi, sine, theta, phi, just like that. The expression you find after deriving ER par rapport à d theta. Let's try and practice. I hope we are not just sitting and waiting for others to find. This is why we are forgetting so easily, because we are not practicing. So let's practice together so that we do not forget. Okay, it's 47. No one has found the answer, because so far I haven't received any responses in the chat box. Okay, saying staff typing says some things. Okay, you can just unmute yourself and tell me the answer if you found it.
You said we differentiate with respect to theta.
Yeah, to theta.
Theta. So that should, according to me, I think that should be D in the direction of AR, or the theta should be that is cos theta cos phi I plus cos theta sine phi j, then minus sine theta k, the direction k.
Okay, Ça, c'est très bien. Quelqu'un d'autre? Did anyone else also try to do it? Les autres, the others, we are being passengers in the classroom. It's not healthy. No one else apart from AL tried to do it. Okay, how disappointing. I wish I'll advance. So, AL, can you just repeat the answer you find, the answer that you found? Now that was the answer for, just give me a sec. That was the answer he got after he derived ER, this expression here, ER par rapport à theta. Okay, he got which answer? You can go ahead.
I said that cos theta, cos phi.
Okay, you can pause there. You can pause there. Just wait. So he said he's found cos theta, cos phi. Look at E theta. Look at the values for E theta. So he's begun with cos theta, cos phi e plus
plus cos theta sin phi
G
j minus sin theta in the direction k.
Okay, exactly. So have you noticed that the answer he got, which is the correct answer by the way, is equal to E theta. So that tells you that the derivative of ER par rapport à d theta is going to give you E theta. When you derive this expression here, ER, with respect to the angle theta, it's going to give you E theta. Okay? So if you had practiced or if you had tried to derive ER, you would have found that. So that is how they found this one here. Okay? D de ER de T, we first broke it down into D de ER de theta fois d theta dt. And then when we derive D de ER de theta or D de ER par rapport à theta, it's given as E theta, as we are from seeing. The derivative of ER par rapport à theta is going to give us E theta. Now, we have one more thing left in calculating the expression for velocity. We have this thing here, d de ER par rapport à d phi, because it's partial differentiation. So when we derive par rapport à theta, we now have to derive par rapport à phi. So again, I want you guys to try to derive ER par rapport à phi, cette fois-ci. Okay, this time around, par rapport à phi. At first, we derived it par rapport à theta. We want now the expression for ER, or the expression for the derivative of ER par rapport à phi. This time around, I invite everyone to try, not just one person. It's very discouraging. I feel as though I'm talking to one person or I'm talking to myself. So please, let's all try. It's for your own benefit. I am gaining nothing from you guys participating. Okay, it's for your own benefit. You have to get used to deriving these things, to working these things. Now is a good time to practice because you might not get a chance like this one. So 3 minutes again. We are at 15:52. We have until 15:55 to calculate the expression for the derivative of ER par rapport à phi. D de ER de phi. Let's go. Let's give it a try. We see what it gives us. Okay, the 3 minutes is up. Has anyone found the answer? They can tell me what they have found.
I found my answer, which was sine theta on negative sine phi I plus sine theta cos phi j plus, I mean, minus cos theta k.
Okay. Nice. Anyone else? Les autres? The others? Our friend has tried. We'll see whether his answer is correct. The others? There's 12 of you guys here. We can't have one person responding every time. We are in this class together and we are all supposed to participate. Okay, so, can you just repeat the answer you gave me?
I said the sine theta on negative sine phi I plus sine theta cos cos phi j and then minus cos theta minus sorry that is plus cos theta.
Okay, so you are very close to the answer. You are actually very, very close, but there's just one thing you've forgotten. Okay, that last term there, what do you have?
We have cos theta.
Cos theta k.
K, yes.
But now it's a constant, not so.
Yes, a constant.
Yeah. So when you derive it, what's supposed to happen to it?
It's supposed to be eliminated.
Exactly. So it's not supposed to be there, not so. Yeah, because theta in this case is constant, and we know k is also constant. So from the expression r, when you reach this last part here, the derivative of cos theta k is supposed to give you 0, not so?
Yes.
Yeah, so the final answer is going to be?
The final answer is going to be sine theta on negative sine phi I plus sine theta cos phi j.
Exactly. So now I want you to notice, is there a common term in those sums that you have? Is there something you can factorize out? I can factor out.
You can factorize out sine theta.
You can factor out sine theta. Yes. So factor out sine theta, then you can tell me the answer afterwards, after you factor out sine theta.
Which is after I factored out negative sine theta.
No, that's factor out sine theta. That's factor out sine theta.
Okay, if we factor out sine theta, then it's going to be negative sine phi. Negative sine phi, that was going to be minus cos phi.
Is it minus cos phi or plus cos phi?
Sorry, plus cos phi, sorry.
Yeah. So I want you to turn your attention to phi here. on the rapport I've shared. This one here that has been circled using the dotted lines. So you see the expression for phi, and you see the expression between the brackets after you factorize sine theta.
Yes, yes.
They are the same, not so?
Oui.
Yeah, so you have phi there. So you have sine theta, phi, n'est-ce pas?
Si.
So when you derive the R par rapport à d phi, it's giving you sine theta, phi, which is what you found, not so?
Sure.
Yeah. So you will never forget that. After the lesson, if you just go through that stuff again, you try to derive them, you will not forget. For the others, I'm starting to get worried. I don't know if you guys are following, but if you choose to just listen, the things, you will forget them almost immediately. You try to practice the stuff to participate. Even if you make a mistake, we're not here to see who's the genius. We're not here to see who's the best. We are here to learn. Okay? And that's how we learn. We learn through mistakes. You make a mistake, you are corrected. Your mind is going to tell yourself, hey man, never forget that. So I don't know why we are not participating, but we really need to participate. So we have our expression for d de r de phi as sine theta e phi. So now we have broken all this down. We have found the expressions. So d de r de t is going to be equal to d de r de theta. We found e theta, so it's going to be e theta, theta point, or rather theta point suivant e theta plus d de r de phi. We found it as sine theta e phi. So it's going to be sine theta e phi. It's going to be phi point sine theta suivant e phi, because d de phi dt is a phi point. So we'll have phi point sine theta e phi, which is going to be the expression we have here. This one, the final one, or this one we found first of all is theta point e theta plus sine theta phi point e phi. Then they found that there as that the final expression for the Vitess on the coordonnées spheric. We had R point suivant E R from this part here. When we did dr dt suivant E R, it gave us R point or R point E R. Then we calculated the next part here, which was R d de E R dt, which gave us this thing here, theta point et theta. When we calculated d de R dt, when we derived R par rapport au temps, it's giving us theta point e theta plus sine theta phi point e phi. So we multiply this whole expression by R, because in the original expression, it's R times this thing. So this entire expression here will be multiplying it by R. That's why we have R theta point e theta plus R phi point sine theta suivant e phi. And this, ladies and gentlemen, is going to be your expression for the velocity in the coordinate spheric. And like I said, in the other velocities, don't rush into memorizing these formulas or these expressions. Know how to find them. First, work on how to find them. Try and find them. Then you can know them by heart as you continue using them. Is it clear? This part for the Vitess spheric.
Kind of repeat.
Where am I repeating from?
Just where from experience.
Okay, I was saying, we're calculating the Vitess in this coordinate spheric. Okay, we're calculating.
Just where from experience. Right there.
I don't know where exactly I should start from. Because I've explained a lot. So when you say just from where you're explaining or where you are from explaining, it's too general. Because if it's the last part here, I was saying don't forget, I was saying don't rush into memorizing the formula. First know how to derive it, how you're going to arrive at it. try to redo them several times. Then as you use the formulas, we'll be doing exercises as you'll be using these expressions, then you can know them by heart. But you risk forgetting them in the exam. So it's better you just know how to find them so that when you forget in an exam or whenever you're going to need it, you can simply derive it, you can get to it, and you are well off and good. But this expression has come from the derivative of R, ER. So we began with a product rule by deriving R par rapport au temps, suivant ER plus R, la dérivée de ER par rapport au temps. Give us that. Then DDR dt give us R point. So this one is not going to give us much of a problem. We can just write R point, R, and forget about it for now. Then we can work on this part here, DDR dt. Okay, so I came to this dapple here where we have the expression for ER, and the expression for ER is equal to sine theta cos phi suivant I plus sine theta sinus phi suivant J plus cos theta suivant K. Then I asked, this expression ER, has it been expressed in terms of T or in terms of time? And you guys told me no. It's been expressed in terms of what? It's been expressed in terms of the two angles, theta and phi. So that means we cannot derive ER directly par rapport au temps because we do not have the expression for ER in terms of time. So what we're going to do is we are going to use the derivé composé, okay? We're going to derive it with respect to the angles, then we'll derive the angles with respect to time, which is simpler for us. Okay, so that's where this now came from. D de R dt fois d theta dt plus d de R de phi fois d phi dt. And why do we have d de R dt, then we have plus d de R de phi? Because in our expression for ER, we have two variables. And when we have two variables and we're trying to derive, we use partial differentiation. And in partial differentiation, what we saw was that when deriving using partial differentiation, you first begin with one variable, you derive the expression with respect to that one variable, keeping the others constant, plus you go to the other variable, you derive the expression with respect to that variable, and you keep the other variables constant, ainsi de suite, until you finish all your variables. So if you have two variables, as in our case, we are first going to derive ER par rapport our first variable, which is theta. So it's going to be d de ER de theta, keeping phi constant, then plus d de ER de phi, keeping theta constant. That's how come we had this expression. Then we calculated d de ER dt. This is where our friend EL, he got the expression, and we found that the expression was equal to E theta. And we saw that d de ER d theta is equal to E theta. And then we also derived d de ER par rapport à d phi, and we found that it was actually equal to sine theta E phi. And that's where we had our final expression for d de ER dt being equal to theta point suivant E theta plus sine theta phi point suivant E phi. And we saw that this entire expression was multiplied by R in our first equation. So the final expression is going to be R point from here, dr de theta, R point suivant ER plus R, this R here, multiplied by the first term here, which is theta point et theta point et theta, plus the same R, this R here, multiplying this expression now, which is phi point sine theta suivant E phi. And that's how come we had our expression. I hope we are going to try to find these things at home tonight, or I don't know, later on in the week, but it's best we do. Is it clear? Okay, so as I told you guys, we are going to introduce another coordinate. Okay, I sent a picture in the group today in the morning. I hope you guys looked at it. If you haven't seen it, you can go back into the the group, and you can check the picture I sent. We're going to look at a new système de coordonnées. So far, we have looked at a système de coordonnées cartésien, système de coordonnées cylindriques, a système de coordonnées sphériques. Okay, so now we are going to introduce another system de coordonnées, which is called système de coordonnées freinées, composante freinée, in French, freinette. Okay, so here we'll be looking at un point matériel en mouvement. When it's moving along a curve, you know, it's moving in terms of, or its movement, its trajectory is becoming a curve. So you're making any curve. It can be any curve that you know of. It can be x squared plus x plus 1. It can be x squared. It can be x to the power 3 plus x to the power 4 plus x to the power 5, whatever curve you're thinking of. But that point, le point M, its déplacement, or its displacement, or its movement, the trajectory being formed is a curve. We are going to use the coordonate freinet to understand, to study, to properly define its movement, to locate its position, to find its velocity, to find its acceleration. We are going to use the coordonate freinet. So that's when we use freinet. We use freinet lorsque on a un point matériel en train de se déplacer avec une trajectoire qui est dans la forme d'une courbe. You know, it's forming a curve as it is moving. Okay, so that's saying soit un point matériel M décrivant une trajectoire C, and we have a courbe. A courbe is a curve dans un référentiel donné. I est la position de M à l'instant initial. So what they're telling us here is, you've seen this curve, guys, and we have our point I there and a point M there. Okay, so they're telling us I est la position de M à l'instant initial. So they're telling us it began its movement at point E, at point I, and it's moved to M. Okay, so the initial position is I, and it's moved to this final position there, M. And they're telling us, on appelle abscisse curviligne. So this is a term you are supposed to know, abscisse curviligne. So they're saying, on appelle abscisse curviligne, which is denoted by the letter S, la mesure de la longueur parcourue le long de la trajectoire C. Okay, so that's the length of the curve that point M has moved. The length of that curve that point M has moved, we call it abscisse curviligne. So here it's moved from E to M. It moved like that. So when we calculate the length of this distance moved by the point M from I to M, we are going to get S, which is called our abscisse curviligne. Is that clear?
Is that clear?
Okay, great. And as you can see here, they're telling you S de t, like S is on function de t, because the point is being displaced with respect to time or in time. So we have it's equal to Im, as you can see from I to M. This length there is the abscisse curviligne, which is S. Then repère de freiner, okay? We have looked at repère cylindrique, cartésien, sphérique. We had la base IJK. In the Cartesian, we had la base RE, E phi, K in the coordonnées cylindriques, and we had la base ER, E theta, et E phi dans le coordonnées sphériques. So this time we're looking at a repère de freiner. So we're also going to have une base that we will be using for this repère freinet. So I want you guys to go to your phones, go into the group, the mechanics group, or if you've already gotten the photo, it's in your gallery, go to your gallery and look at that photo I sent. It's written Freinet, Serre formulas. Okay, so these two French mathematicians, one was called Freinet or Freinet and Serret, they are formulas. So there they have tried to show you how the base vectors in this repère Freinet, how they are oriented or how they appear to help you with your imagination. I went to Google and looked it up so that I can send you something you can look at as I explained, because the coordinate freinet tends to confuse many of us. So at least you have a mental picture even as we'll be studying it. So look at it. Okay, so they're telling us le composante de freinet du nom du mathématicien J.F. Freinet sont relatives au trièdre, okay, défini en un point de la trajectoire par les trois vecteurs unitaires suivants. Okay, so la base this time, the base is defined by these three unit vectors. We already know for it to be called a base, its vectors have to be unit vectors and they have to be orthogonal in most cases. Yeah, so this time around, our base is going to be T. Okay, so I hope you guys are looking at the picture center.
Yes, yes.
Yes, lovely. So you're looking at the picture. So we have T. I'm sure you guys can see T. T, the direction of T there, that arrow with a T at its head. So that's the tangent à la trajectoire. So that's a tangent to the curve, as we've already defined. In the coordinate framework, we are studying a point M which is in movement, and its trajectoire is a curve. Okay, so when you're dealing with curves, you have the tangent to a curve. And we know tangent to a curve, tangent is a line that touches a curve, that touches a circle at one point. Okay, so that line there that touches that curve at the point M is the tangent, and the vector that's oriented in that direction of that tangent, we call it T. And this T is always in the direction of movement. Okay, it shows you the direction of movement of that point. Okay, it's always in the direction the point is moving. It's a T. So I'm sure you guys can see T in the diagram. Then we have the vector N, vector unitaire N. I'm sure you guys can see it from the picture. C'est le normal à la trajectoire. N, c'est le normal à la trajectoire orientée vers la concavité. So when you say concavity, it's like going inside the curve. Okay, as you can see where N is going like it's going inside the curve. So you guys can see that that's the concavity. It's like you're going inside the curve. And then we have the B normal. Normally the B normal is a bit hard to picture, but you just picture it as being perpendicular at the same time to T and also N. That's why they call it B normal. It's normal to T and normal to N itself. Okay, it's the normal. And I even told you guys, normal is like meeting something at perpendicular. When you say ça c'est normal à quelque chose, it's like they're meeting at 90 degrees. So we say normal à la trajectoire. Normally the trajectoire is being given direction by T. So when they say N, c'est normal à la trajectoire, it's like N is perpendicular to that T. And then when we say binormal meaning it's normal to T and normal to N. Okay, so we know that T vectoriel N is equal to B. I explained this when we said they are direct. When we said R vectoriel E phi is equal to K. When we said R vectoriel E theta is equal to E phi. So they are direct like that. So the same thing, T vectoriel N is going to give us B. But what you should know when you're trying to picture the binomial, just picture it as being perpendicular at the same time to T and to N. So you can try to say T and N are in the same plane, and B is like perpendicular to that plane. The way we had X and Y in the same plane and Z perpendicular to that plane. So we had Z, X and Y in the horizontal plane and Z in the vertical plane perpendicular to it. So in this case, we cannot say N and T are in the horizontal plane. It depends on how your curve is oriented. But if you want, you can imagine it as being in the horizontal plane and your binomial as being in the vertical plane. But it's not always the case. I can have, for example, my curve leaning against the wall. My B there is not going to be in the vertical plane. It's going to be like coming out of the wall. Okay. As you can see from the picture there, you have like N and T, they are aligned on the page, and you have B appearing to be coming out of the page. You guys get that, huh?
Yes.
Okay, good, good. Nous supposons que la courbe est plane, soit un point matériel occupant la position M et M'. Now about studying the movement of a point M. So we have, nous supposons que la courbe est plane, soit un point matériel occupant la position M et M' sur la courbe-ci, respectivement aux instants T et T' equal to T plus delta t. So what they're telling us here, we have the point M, and that point M, it's at time t. Then it moves to M prime, and at M prime, it's at time t prime, okay? And t prime is equal to t plus delta t. So we have mm prime being equal to mi plus im prime. So try to picture something like this. You have this figure here. You have m there, and imagine maybe m prime is somewhere here towards the end of the curve. Okay. So we want this distance m prime, m prime. So it's like you moved from im, then you moved from m to m prime, or it can be the difference between im and this one, im prime and im is going to give you this difference here. So what they're telling us now is mm prime is equal to mi plus im prime. So you move from m to I, and then from I to m prime. It gives you this distance there. Or if you want, you can picture m prime on this other side here, so that it's easier for you to imagine. You have m prime there, so you have m prime being equal to from m to I, and from I to m prime. Just for imagination's sake, since it's not denoted, it's not shown where the m prime is, so it's just up to you to picture something to help you understand. As I told you, in mechanics, you're going to use a lot of your imagination. Try to imagine things, try to see things. If things are not clear in the polycopy, try to see them in your head. You understand them better like that. So you have mm prime being equal to mi plus im prime. Now, when you play around with vectors, okay, when a vector is going in one direction, when you turn it in the opposite direction, it's just equal to the same vector, but this time with a negative sign. So if I have mi, it's equal to im, but negative, okay? So mi is equal to negative im. That's how you just play around with vectors. They are parallel, but in opposite directions. So it's equal, but just with a negative sign. So at first we had mi plus im prime. So if I turn this mi, I just turn it in its opposite direction, it's going to become im, and it's going to be negative im. So we'll have this being equal to im prime minus im, which is equal to, we were told that the distance between I and m is equal to s. That implies that the distance between I and m prime is going to be equal to s prime, okay? We're just trying, instead of using I and m every time, it sounds a bit complex. We just use Labsis-Kevelin, which is equal to s. And now we know that s is just simply the distance moved from one point to another on the curve. So im prime is just the distance from I to m prime, just that length there, which we will call s prime. The Labsis-Kevelin there, so it's going to be s prime. And im, we already know im is equal to s. So here we'll have s prime minus s, which is simply the final distance minus the initial distance, so to say, which is equal to delta s. Whenever you see this delta in mathematics, it's mostly representing change in something. Okay, so it's like you are somewhere and you moved to a new point and you want to find the difference in that change. So you have delta s. So s prime minus s is going to be equal to delta s. Just as we looked at before, we had om minus om prime. It gave us delta om, or which was equal to m prime. Okay, so to help you imagine, imagine this curve here, this curve, you're going from m to m prime, and you can picture your I maybe somewhere here. So from I, you move to that and then to that. So you had m and you have m prime, and you're moving from m to m prime on this curve here, this curve here. This is your s, your Labsis-Kevelin from m to m prime, or delta s rather, okay? This is your delta s from m to m prime, delta s there, Labsis-Kevelin. And then you have your chord, when you have an arc, like this one, the line, the straight line that connects the two ends of the arc is called the chord. You guys that did additional mathematics remember this. For those of you that have never done additional mathematics, well, here's something to add to your vocabulary. We have what we call a chord. When you have an arc like this one, this arc, M prime, the line that you draw between the two extremities of that arc, from one end of the arc to the other, that line there, the shortest line you draw there, we call it a chord. Okay, so we have this chord M prime. And what they are going to explain to us here in this next part is that M prime est un très voisin de M. It's like we're studying 2 points that are very close to each other on this curve, okay? They are very close to each other. On peut confondre D de OM et D de S. D de OM is this one here, the code. When we are studying OM and OM prime in the coordonnées Cartesian, coordonnées spheric, and whatsoever, we're dealing with straight lines. You guys remember that, huh? So when we draw a straight line from M to M prime, it's like we have what we're dealing with there, the D de OM or the M prime. And then in the coordonate friend, now we're dealing with curves, okay? We're dealing with curves, les abscisses Kevelin. And that's the curve here that we have M prime. Now they're telling us that M and M prime are very close to each other. Like they are pretty close to each other. So if you have 2 points that are close to each other, the arc and the chord, they're almost going to be equal to it. I don't know if you guys can imagine that. Imagine I have this point here, M, and then I draw M prime just right next to it. Can you differentiate between the arc and the chord in this case? No, they are almost the same. It's like when you draw a line between them for you to get the chord, it's just going to be interfering with the arc itself. So it's like they're almost the same. The arc and the chord are almost equal because M and M prime are close to each other. They are very close to each other. Très voisins, meaning they are very close to each other. So what they're telling us is on peut donc confondre. When we say on peut le confondre, it's like we can confuse them or we can take them as equals. In place of one, we can use the other. When they say on peut confondre, ces deux termes, means in place of one, we can get the other because they are equal, so to say, in some sense. So, and if they are equal, that means D de OM over the S is going to give you a 1, the magnitude of these two. Since they are almost the same, on peut les confondre, that means their magnitude of the magnitude of their division is almost the same. If I tell you A is equal to B, and then I divide A over B, it's going to give me 1 because those two are equal. So this is one expression we'll keep as le module de D de OM over the S is equal to 1. And then they're telling us lorsque M' tend vers M, D de OM sur DS est un vecteur tangent à la trajectoire en M. So they have told us now that this here, D de OM sur DS est un vecteur tangent à la trajectoire en M et son module tend vers 1. On introduit T was the trajectoire, the tangente. T, c'est la tangente telle que T égale 2 de OM sur DS. So, again, here, it's a matter of imagination, okay? It's a matter of imagination. So let's say I have M and I have M prime, very close to each other, very close to each other. As I told you, when you try to draw the chord M prime, when you try to draw it there, it's just going to be the same as the arc. It's like you're not going to be able to see the difference between the arc and the chord because the 2 points are so close to each other. So it's like the line you draw there, the line you draw that will be acting as a chord this time. It's just going to be the same as the tangent also because the two are very close to each other. The line that you are going to draw is going to be on the arc, so to say. It's going to be almost on the arc that you have there. So it's just going to be like the tangent. And that's why they're telling you that D de OM over DS est un vecteur tangent à la trajectoire. Okay, c'est un vecteur tangent à la trajectoire. And because we have its module being equal to 1, okay, because its module is equal to 1, and we know that T, here when we introduced T, it was part of la base du repère Freinet. And we know that the vectors in the base are equal to 1. And we have this vector here with a module equal to 1, d the OM over the S. So it becomes our tangent, okay? I don't know if you guys have seen it. You really have to try to imagine these things for you to see them and to understand them, or you can just get them as gospel truth the way they are. You just memorize, say, do the OM over the S is equal to 1, and then you say, okay, so my tangent there, the vector T, is going to be do the OM over the S. You just get them as they are and you keep them in your mind, but you easily forget them like that. That's why I would like you guys to try and imagine, to try and see where they are coming from and why that is so. And sorry about that. Okay, sorry about that. There's some noise in the background. Yeah, so I want you guys to try and imagine, to try and picture and see where these things are coming from, okay? So when you try and draw, like here, when you get a point M prime very close to M, very close to it, the line that you draw, that is supposed to be your chord. It's almost going to be on the arc itself, and acting is going to be like the tangent at that point. And that's why we are getting T. That's why we have chord T as being equal to d the OM over the S. And another reason why it's convenient that T should be equal to d the OM over the S is because the module of d the OM over the S is equal to 1. Okay, and we know that T, c'est un vecteur unitaire, alors son module aussi égale à 1. So we have T, you take note, it's even highlighted there in the box, saying T égale à 2 de OM over the S. It's important that you remember this. And then they're telling us, on construit alors le repère de freiner à partir de ce vecteur. On désigne par N le vecteur unitaire situé dans le plan de la trajectoire et porté par la normale à T. I told you normal at T is like perpendicular to T. And we saw from the definition of N that it's directed in the direction of the concavities, like it's going inside the curve. Okay, dirigé vers la concavité de la trajectoire. From the picture I sent you, you guys can see the direction in which N is going to. Okay, then they're telling us on 3 dimensions, jusqu'à maintenant, we just have 2 vectors. We have the vector T and we have the vector N. So it's like we are still in the 2-dimensional space. Now, in the 3-dimensional space, we introduce a 3rd vector. On complète la base en formant le vecteur T vectorial N, which is equal to B, the binomial that I already explained to you guys. And finally, we are going to have our base, la base du coordonnée freiné is T, N, and B. And it constitutes la base directe de Freinet. Then we come to the vector Vitess. Vecteur Vitess. Le vecteur vitesse V du point M par rapport au référentiel R égale, as usual, it's d the OM over dt, the derivative of the vector position, which is going to be equal to, again, we are going to use the vector, the derivative composite. It's like we're going to use the composite derivative, okay? D the OM, instead of saying d the OM dt, which is going to be a bit hard for us to derive because we don't have the expression of OM on fonction du temps. So we are not going to be able to derive d the OM dt. So what we're going to do again, we're going to decompose it. So instead of saying d the OM dt, we'll use d the OM ds multiplied by the s sur dt. Okay, and d the OM ds, we know what this is equal to. D the OM ds is here. We have this expression, d the OM ds is equal to t, the vector tangent. So d the OM sur ds is going to be equal to t, and we have our t there. And then we have the s sur dt, as this one here is going to stay like that. And this is going to be a final expression for the velocity. V, vitesse du point M par rapport au référentiel R égale ds dt fois the vector tangent t. Just like that. As simple as that. This is going to be the expression for the vector vitesse. Okay? And then when you calculate the magnitude of the vector vitesse, when you introduce the magnitude, it's like you introduce magnitude on the left-hand side and magnitude on the right-hand side. what's the magnitude of t? The magnitude of t is what?
It's 1.
1, exactly. The magnitude of t is 1. So if we do vector, the module du vector v, it's like you have module of v this side, then you have module of ds and module of t. And the module of t is equal to 1. So it's like this 1, since we're multiplying, it's going to disappear parce que c'est un terme neutre. It's a neutral term. It's not going to change anything. So the t is going to disappear because it's a 1. And we'll have module of the Vitess just being equal to ds over dt. And when we talk about the module of the Vitess, we can simply just denote it with v, okay, just v, with no flash on top, because the flash is for the vector. But since we are doing the module, this time we just want the size of the velocity and not its direction, its sens, and all that stuff. We're just dealing with the module. Module c'est un scalaire, so we just have v, okay? So v is equal to ds sur dt. So you guys can keep this in mind. ds over dt is equal to v. ds over dt is equal to v, where v is the magnitude of the velocity, okay? And the magnitude of the velocity is equal to ds over dt because the velocity itself, the vector Vitess, is equal to ds over dt suivant le vecteur tangente t. So when you introduce magnitude of the vector Vitess, the t is going to disappear because its magnitude is equal to 1, as you guys have told me. So we call it la norme de vitesse n'est autre que la dérivée par rapport au temps de l'abscisse kevélin. Okay, so when they ask you what's the module of the vector Vitess, you just tell them it's the derivative with respect to time of the abscisse kevélin, which actually makes sense. Okay, because the abscisse kevélin is the distance or the displacement moved by the point matériel. Okay, and when we want velocity, it's like we want the rate of change of the displacement with respect to time. So if I want the module of the Vitess, it's just going to be simply the derivative of the distance moved with respect to time, because that's the rate of change of distance with time. I don't know if that makes sense to you guys. V being equal to ds over dt, the module of V being equal to ds over dt, the derivative of the abscisse kevélin with respect to time. And the abscisse kevélin is simply the distance or the displacement moved by the point M. So we are simply just calculating the rate of change of displacement with time, which is what the definition of the Vitess is. Clear?
Oui.
Okay, lovely. So you guys should revise this. So that's the coordinate framework. So for now, just retain this formula. The Vitess vecteur Vitess égale ds dt suivant t. Okay, vector Vitess égale ds over dt suivant t. If you want to remember it well, you can also picture a circle. I don't know if you guys ever did what was that topic in physics? We're calculating the velocities. I think, yeah, it was when we're calculating velocities and accelerations in physics in a circle. They used to tell us that the velocity is always oriented in the direction of the tangent at that point. Okay, in physics, what they taught us that the velocity of the point on a circle that is moving, its velocity is always oriented in the direction of the tangent. So that's why here, the Vitess of the point M on a curve, because a curve is almost like a circle, but just not completed. Okay, so it's going to be equal to the velocity, which size is the derivative of the abscisse kevélin, or its distance moved with respect to time, and in which direction? In the direction of the tangent at that point. That's why the formula is like this. The Vitess, the direction of the Vitess is in the direction of the tangent. That's why we have a vector tangent there, and then we have its size being equal to ds over dt, which is just the rate of change of displacement on that curve with respect to time, which gives us the speed quite conveniently. And that's that. We have 20 more minutes to go. Good. We can try and look at vector acceleration. I think we'll finish the first topic tomorrow. Next week, we'll be doing questions. So, vector acceleration. Le vecteur accélération du point M par rapport à R à l'instant T est la dérivée à cet instant du vecteur vitesse par rapport au temps. Another thing is, some of these things are just vocabulary, you know. If you understand what it means in English or in French, calculating it becomes easy. Sometimes calculating or understanding some of these things is a bit hard because we do not know what they mean. I noticed this yesterday. I was following Analyse with you guys, and borné, the word borné confused a lot of people. But you find that the word borné is even used in French, just in normal conversations like ça c'est borné par ça et ça. So if you just know what the word borné means, it's like you even understand what it represents in mathematics. It's that there's something blocking it on one side and another thing blocking it on one side. So that thing is in between two things. There's a majorot on one side and the minorot on one side. So it's borné par ça et ça. You understand what that means. So when we tell you vector, vitesse, what's the velocity? You ask yourself, what's velocity in English? When we say the velocity of this car is this and this, it's moving at this and this velocity. What are we talking about? Oh, it's the rate of change of distance with time. How its distance is changing in time. That is velocity. So now we come to acceleration. Now you ask yourself, what is acceleration? When you say, oh, this car accelerates at this and this acceleration, what do they mean? Oh, this car has a very good acceleration. They tell you, oh, you see this BMW, in 5 seconds, it can already be at 100 meters per second. So you know, oh, so within a space of, within a time of 5 seconds, its velocity would have already changed from 0 to 100. Ah, okay. So what they're telling me is acceleration is the rate of change of velocity with respect to time. Ah, okay. So that's the acceleration. It's just the rate of change of velocity with respect to time. So if you give me a time of, let's say, 3 seconds, and they ask me, what's my acceleration? They're asking me, how did my speed or how did my velocity change in those 3 seconds? Maybe at the beginning of the 3 seconds, I was moving at 30 kilometers per hour. And at the end of the 3 seconds, I found myself moving at 200 kilometers per hour. So I moved from 30 kilometers per hour to 200 kilometers per hour in 3 seconds. Oh, wow, that's impressive. My acceleration is really good. So that's what it represents in English and in French. Acceleration is simply the rate of change of velocity with respect to time. So that means for us to find the acceleration, we'll simply be just deriving the velocities that we have found. That's how simple these things are. So we have already calculated the velocities in the coordonate Cartesian, coordonate cylindric, coordinate spheric, and in the coordinate finite now. We already have the expressions for the velocities. So for us to find the acceleration, we'll simply just go back to those expressions for the velocities and derive them une fois de plus, a second time, and we are going to get our expressions for the acceleration. That's why I told you guys at the beginning of the lesson today that today we'll just be doing calculations. It's just calculations, ce n'est que le calcul, because I've already given you most of the concepts you need in cinématique du point matériel. So in this box here, they have highlighted the general expression for the acceleration. It's equal to dv dt, the derivative of the velocity with respect to time. Or if you don't have the velocity, you can derive the vector position or the displacement twice. So when you derive it the first time, you'll be going to the velocity. Then you derive it the second time, you'll be moving from velocity to acceleration. Alors, c'est la même chose. Soit vous dérivez la vitesse par rapport au temps une seule fois, soit vous dérivez le vecteur position par rapport au temps 2 fois. Vous calculez la dérivée seconde. So they call it in French, dérivée seconde. You derive it twice. Potato, potato. Same thing. So we begin with coordonnées Cartesian. As usual, the coordinate Cartesian is so boring. There's nothing in it. There's nothing to do in it. Just 1-2 lines, you're done. Okay. So we have our vector position, or M, being equal to xi plus yj plus zk. Ça, on l'a déjà fait. And then we have our vitesse, M, par rapport à R. We had already calculated this. We said it simply x point I plus y point j plus z point k. So now when you're calculating the acceleration, you are just going to derive the vector position. Sorry, not the vector position, but the vector Vitess. So when we derive the vector Vitess, we are going to have x. The vector of Vitess is x point E, y point J, plus z point K. So the acceleration now, we're just going to derive them twice. So we'll just put 2 points. So it's going to be x2 point, so you just put dot dot, y2 point, dot dot, z2 point, dot dot K. And that's it. Then you found the acceleration in the Cartesian plane. Very plain, very basic, very boring. We advance. This has x2 point E, plus y2 point J, plus z2 point K. And as usual, as I told you guys, that x, it can be anything on the x-axis. They're just telling you that you are moving along the x-axis, okay? So when you write x point, I'm just showing that you derived that x coordinate that's changing. We don't know what it is, but we have derived it one time. Then when we say x2 point, it's showing us that, at least we derived it twice. Okay, so in y2 point, we've derived it twice. And the acceleration is la dérivée seconde du vecteur position. That's why we have 2 points. We have derived it twice. Is it clear for the coordinate Cartesian? Very basic, very plain, very boring. Is it clear? So now we come, okay, lovely. So we come to the coordonate cylindric, okay? Coordonate cylindric polaire. Now the expressions are starting to get longer, longer and a bit more complicated, but the calculations are still the same things. C'est la même chose, les mêmes choses qu'on vient de faire. It's not going, nothing has changed. We will be decomposing the derivatives that we have. We will be deriving angles par rapport au temps. We'll be deriving rho par rapport au temps. We'll have rho point, rho 2 points, phi point, phi 2 points. Same things. So if you understood what we did on the vector Vitess, the acceleration should not confuse you so much. It's going to take you a bit longer to find, but it should not confuse you much. So let's get right into the nitty-gritty. First and foremost, the vecteur Vitess du point M par rapport au référentiel R dans le coordonnées cylindrique égale, we found rho point euro plus rho phi point e phi plus z point k. Okay, so now we are going to derive this. So we're going to begin with the first term. The first term is rho point euro. Rho point euro. This is a product, and we're going to use the product rule. It's like the third time today I'm mentioning the product rule. I'm sure you guys must know what it is. So the product rule, we are first going to derive a rho point, keeping euro constant, and then we'll come and keep a rho point constant, and we are going to derive euro par rapport au temps. So we begin with the derivative of rho point par rapport au temps. So since there's already a point here, we'll just put another point. So it's going to be rho 2 points. Okay, it's going to be rho 2 points suivant euro, and that's the one we have here. And then we are now going to derive euro. We're going to have a rho point, la dérivée de euro. And then 2 de euro dt. Here we have a rho point, 2 de euro dt. So we come here, 2 de euro dt. Ça, we have already calculated it. We calculated it when we're calculating the Vitess, and we decomposed this derivative into 2 de euro de phi, because the expression that we have for euro has been expressed in terms of phi. So we decompose this derivative into 2 de euro de phi fois de phi dt, because we have euro in terms of phi, and we can simply derive this one. And when we derive 2 de euro de phi, we find e phi. Ça, on l'a déjà démontré. Okay? We showed this. 2 de euro de phi gave us e phi. And then 2 de phi dt is phi point. You simply just write phi point. So when you derive 2 de euro dt, is going to give you phi point e phi. So here we have rho point phi point e phi. Rho point phi point e phi from this expression here. Then we move on to this expression now. This expression, the second one, there's 3 terms. So as usual, we'll use the product rule, but this time we'll use it 3 times. So we'll first derive rho and keep these two constant. Then we'll derive phi point and keep rho and E phi constant. Then we'll come and derive E phi and keep rho and phi point constant. Okay? It's a bit long there, so follow me, don't get left behind. So we'll begin by deriving rho and keeping these two constant. So when we derive the rho par rapport au temps, that's going to be rho point. That's why we have rho point, phi point, E phi. We've derived rho and we've kept these two constants. So you see phi point, E phi point, E phi. And we've derived rho. That's why it's given us rho point. Then next up, we are going to keep rho constant and E phi constant and we'll derive phi point. Okay? And when we derive phi point par rapport au temps, that's going to be phi 2 point. We've derived it twice now because we derived it the first time, give us phi point. And when we derive it the second time, it's going to give us phi 2 point. So it's going to be rho phi 2 point E phi. Rho phi 2 point E phi. That's why we have the rho phi 2 point E phi. And then finally, we are going to derive E phi, keeping rho and phi point constant. Okay, so we'll have rho phi point 2 de E phi sur dt. That's why we have this here, rho phi point 2 de E phi sur dt. So now we're going to calculate 2 de E phi sur dt. So 2 de E phi sur dt is equal to, again, you're going to look at the expression that we have for E phi. The expression that we have for E phi is this one here. E phi is equal to minus sine phi e plus cos phi g. This one is not in terms of time. It hasn't been expressed in function du temps. So we can't derive E phi par rapport au temps directement. We'll have to decompose it into a variable that is being expressed in, and then we use a derivé composé to derive that there. So since we have E phi written in terms of phi, we'll have 2 de E phi, de phi multiplied by, and since we have introduced de phi here, we'll introduce de phi there, so that when they simplify, we are left with 2 de E phi over dt. So we'll have 2 de E phi over de phi multiplied by de phi over dt. And 2 de E phi over de phi, this I already explained to you. It's like you are making E phi rotate 90 degrees in the anti-clockwise direction. So it's going to become minus rho. If you revise your work, you are going to find this rule. When you derive E phi par rapport à phi, it's going to give you minus E rho. And then when you derive phi par rapport au temps, it's going to give you phi point. That's why we have minus phi point E phi. This expression here, minus phi point. So not E phi, but E rho. Minus phi point E rho. So la dérivée de E phi par rapport au temps, c'est minus phi point E rho. So when you come here, you write minus phi point. So you have minus phi point carré because you have phi point and phi point there. So the phi point will be squared suivant E rho. And then finally, you'll be deriving Z point because K is a constant. Ça, c'est fixe. Je vous ai déjà expliqué que IJK, c'est une base fixe. Alors, les vecteurs unitaires I, J, K sont tous fixes. Leur dérivée égale à 0. So we have Z point, la dérivée de Z point par rapport au temps is simply going to become Z2 point, comme on a vu dans le coordonnées cylindriques. And then finally now, we rearrange the like terms. Those that are going in the same direction, those following E, we put them together. Those following E phi, we put them together. Those following Z, we put them together. Or those following K or EZ, sorry, we put them together. So this is going to be, we have this one here, rho 2 point, suivant E rho. And then we also have this one here, which is rho phi point carré. It's actually minus rho phi point carré, suivant E rho. Also, it's following E rho. So we'll have rho 2 point minus, because of this minus here, rho phi point carré to the power 2. Parenthesis, suivant E rho. That's why this has come from rho 2 point E rho, and we have moins phi point multiplied by rho phi point suivant E rho. This gives you that. Then you collect those following E phi also. We have this one following E phi, and we also have this one following E phi. And also this one here that we calculated from this expression here, it's also following E phi. So we'll have rho point phi point E phi plus rho point phi point E phi. You notice that these two are the same thing, these two, because this one is rho point fois phi point suivant E phi plus rho point fois phi point suivant E phi, like that. So when you add this plus this, it's just going to give you 2 times this. So it's just going to be 2 rho point phi point E phi plus rho phi 2 point E phi. That's why we have rho phi 2 point plus 2 de rho point phi point suivant E phi, like this. This term here between parentheses is coming from this, and that. They are all following E phi. And then finally, we have Z2 point. Z2 point suivant EZ. This one is direct. And your final expression for the acceleration becomes rho 2 point minus rho phi point carré euro plus rho phi 2 point plus 2 rho point phi point suivant E phi plus Z2 point suivant EZ. That's your expression. Then on coordonnées polaires, as I have already emphasized several times, from cylindric to polaire, what just changes is the z. The z becomes equal to 0. So you just eliminate the z coordinate there. So you just be left with rho 2 point moins rho phi point carré suivant euro plus rho phi 2 point plus 2 de rho point phi point suivant E phi. Et ça y est, that's going to be your expression for the acceleration dans le coordonnées cylindrique. Ça aussi, you are supposed to know how to get to it. So you guys should go and practice deriving these expressions. So go into the coordonnées cylindrique, get the vector position. That one you're supposed to know by heart by now. So you know it's equal to rho euro plus zk. Then you say the Vitess is going to be the derivative of that. So you are going to derive rho euro plus zk. You get your Vitess. Then when you get your Vitess, you now calculate the acceleration by deriving the Vitess. So you derive the Vitess and you arrive at your acceleration. You go into the spheric. The spheric at my school, those of you coming to GGM, you won't calculate the acceleration for the coordinate spheric, but I'm sure in other schools you do it at the ENSA and whatever if other FSTs exist, or wherever you go, maybe you're going to do it. But those of you going to like SVT that don't go deep in the mechanics, I doubt you also do the acceleration for the spheric part, but we'll do it here nevertheless. It's better we're safe than sorry. So we'll end here for today, but we'll continue tomorrow. We'll calculate the acceleration Freinet, and then we'll also calculate l'accélération sphérique. Then after that, we'll go to the last sub-chapter of this one, which is changement du référentiel, after which we'll be done with this. And next week, inshallah, we'll do some exercises, maybe 2-3 questions, just to help you guys understand. And that will be it for mechanics. Yeah, so up to this point, are there any questions? Yes, whenever you want to calculate the acceleration, it's the second derivative of the vector position, okay? Second derivative of the vector position OM, but the first derivative of the Vitess. So if you're calculating acceleration using the Vitess, you just derive the Vitess once. But if you're calculating the acceleration using the vector position, when you're starting from OM, you have to derive it twice for you to get to the acceleration. Is it clear, MH Ria? I don't know if it's Mariah or what. Because we are not revising analysis and mechanics, or analysis, the algebras, whatever modules you have are taking so much of the time that you are not even sparing a second to do mechanics, but that's going to be a bad idea if you are doing that. just revise all the modules equally. You never know where your luck lies. Maybe you might need mechanics to help you advance, or these same mechanics, you can try and get a 19 so that you get more marks to raise your moyenne or your average score. So let's revise. Let's revise, because I'm asking you guys. Last week I asked you guys a simple trick question, and only a few were able to get it. The rest, it's like they didn't know what was happening. Today, I asked you guys to just derive, not even really apply mechanics, just derive, just mathematics. And only one person out of the 12 we were was responding, which was another concern. So I don't start bombarding you guys with a lot of work, because I know you guys are already getting a lot of work in the mathematics modules, the analysis and the algebras. You guys are getting a lot of work. So I don't want to give you work also in mechanics, because then you'll just will break you down. You won't have time to yourselves. Okay, so I'm trying not to give you so much work, but it seems that me not giving you work is making you neglect this module. So let's just revise. Okay, let's revise. When we do this, let's revise. So let's revise this so that tomorrow you guys won't be as lost as today when we were trying to derive the expressions and all that stuff. Okay, are there any other questions up to this point?
Miss, I'm just asking for the other polycopy you are using. I don't think we have.
I sent both of them in the group.
I couldn't find it. I don't know if you can send it again. Just
Okay. Which one is it? The
other one.
The first one.
No, this one where there is
This one.
Coordonnées Cylindriques. Yeah, that one.
Ah, okay. Yeah, but I sent it, but I'll send it again. Let me send it now. Okay. Are there any other questions before we go? Okay, silence is golden and it's taken as no questions. Everything is clear. I hope you guys have understood what we're doing today. If that's the case, on se verra demain. Je vous souhaite une très bonne journée. J'espère que vous allez réviser tout ce qu'on a fait aujourd'hui. Yeah, I guess that's pretty much it from me. Goodbye. And I'll be ending the meeting now.